Got this. All right. So I'm Vijay Rane. I'm a Prime Minister Research Fellow in IIT Delhi and also in the University of Queensland. So today we are here to discuss some problems uh, from the week 2 of the course Essentials of Oxidation, Reduction and Carbon-Carbon Bond Formation uh, and its application in the organic synthesis. So as we have already discussed some problems in the on last Tuesday. And today also we will discuss some more problems, right? So these are the some topics which are covered in the second week. So which involve, so I'll just try to, yeah, all right, which involve the selenium-based oxidation of the ketones and also the sulfoxide sulfinate rearrangement reaction, or also uh, Mislow Ivan rearrangement reaction. This kind of reaction that we have already they studied uh, in this week, and further some mechanistics as well as the stereochemical aspects of these rearrangement reactions. And we have saw some examples in which the practical application of this reaction have been performed in the synthesizing some drug molecule or some natural products. And again, we have see the 1,2-keto transposition as well as the Shapiro reaction and the Dobbin Michno rearrangement and a case of 1,3-di transposition. And further, we have started a new topic on the Des-Martin per iodine, in which we have seen the hypervalent, not hypervalent iodine, but iodine-based reagent, IBX, as well as the Des-Martin per iodine oxidation reactions. So before going to start the session, does anyone have any doubt regarding this the topics that are covered in the week 2? So we'll take the that question first if anyone have any doubt, and we'll directly move to the some problem that I have added in the slides that we'll discuss. Yeah, if you have any doubt, you can just keep noted that doubt, and also you can interrupt me in between, and you can ask that time also, no issue. So if anyone have no any doubt, then we'll just start from the some mechanisms and some examples we'll see. So the many questions in the assignment 1 is based on the humoral rearrangement reaction, and this is the general mechanism for the humoral rearrangement. So which involve uh, sulfonate as a sulfoxide as a starting, and also acetic anhydride. In place of acetic anhydride, it forms such compound which have the RS as well as the O-acetyl group comes from the acetic anhydride, and this is another R2 which is comes from here. So this kind of reactions are involved in the fumarate rearrangement. So this is the mechanism. So if you look at the structure of the sulfoxide, so we can do the partial charge separation in this sulfoxide, and this negative charge attack on the acetyl part of the acetic anhydride, followed by the, yeah, it will be a kind of acetyl transfer reaction, and again, uh, yeah, so it formed the acetyl compound, this intermediate, and as we see the in the reaction, the OAC minus which leaves from the acetic anhydride, which attack to the proton, attached to the sulfur, and abstraction of proton takes place, followed by the intermediate formation, which involve the cationic sulfur. And if you have any kind of nucleophile in the reaction, especially in this reaction, there is a O-acetyl, so which attacks to the positive charge, it gives the formation of the product. So we see this reaction, and also there are some applications which I just kept from the one of the. I will add the PDFs of these some books in the OneDrive, and hopefully you guys are able to access that OneDrive. So, uh, or else I will send that link of the OneDrive in the chat box that so that you can able to access that one. So remind me at the end of I have a PDF of the many books. So if you need any books in the PDF format, you can just put the name of that book in the comment section. So I will add the PDF of that book in the OneDrive, and I will also provide the link for that OneDrive. All right. And also these are some already seen some methods to make the organocilium compound, and here already summarized in this slide. You can look that slide from the OneDrive, right? Further, one reaction that we have studied in this second week is sulfoxide sulfonate rearrangement reaction, also known as Mislo-Ion rearrangement reaction. So, which involve, let's say we have some compound. Let's start from the beginning. So, let's say we have such a compound which has the alcohol, and if you react that, sorry, it OSR, and which is present in equilibrium as you have seen in earlier in this format in the form of, so this sulfane which can be present in this form as well. So R or AR, anything. So here there is a sulfur, and also when this sulfur, obviously it will be a, let's say, positive and negatively charged. Let's say I will directly write the charge separation here, and which attacks to here followed by here and this bond cleavage. So it can be transferred this OSR in this form, right? And so this is kind of rearrangement reaction occurs in this 2,3 sigma topic. Rearrangement occurs from this step to this step, right? Uh, yeah, and if there is any kind of uh, thiophile or any kind of such reagent present in the reaction that that can substitute this RSH to the and convert this compound into the OH alcohol, such alcohols. And uh, so this is the sulfin sulfonate rearrangement reaction. This is the general mechanism. Here also the same mechanism that just drawn here as I have shown earlier. So you can refer this slide as well. And someone asked the question, so why uh, in the yes, anyone have any question here? So I thought someone has unmuted. Right. So this is the one of the questions someone asked. The question was the the stereochemistry of this OH, which is asked in the question QA and section of this on the NPTEL portal itself. So why this is the stereochemistry in this one? So we'll directly go step by step from here. So in this one, if you look at this is the this reaction. In this one, what happened? This is the alcohol, right? So this alcohol when react with the this compound, it form OSPH, right? So if I just take this instead of entire whole molecule, if I just add only few part, or if you just go back to refer our earlier the mechanism that we have shown. So if you have such compound, so this hydroxide transfer from one position to three position that can be takes place. So here also it is happen in the same manner. So so it form initially the SPH, then it converted into the sulfoxide. So first step is the formation of SPH. So this OSPH bond. Better I will take it on the new new slide and also take the same one. So in this one, first what happened? So I will write this only this part only from this molecule. right? Initially it is alcohol, right? So it forms, I have to write the six numbering. It forms OSPH, and as I have seen earlier, which is in equilibrium with this kind of uh, form. So this will be converted into the double bond sorry, is double bond OPH, and further this double bond OPH can again form the partial charge separation here, right? So O negative, yeah, O negative and S positive, and this will be a 2,3 sigma tropic. So it forms is the CH2O and SPH. So this is getting formed in this step, right? And again, uh, as we converted this from SPH to S double bond OPH, the similar happens here also again, and this forms a intermediate, this one, right? So first happen, the first step is this one, formation of OSPH bond. The second step is formation of S double bond O just by tautomerization, and third step is this 2,3 sigmatropic reaction, that is the rearrangement, that part. And again the fourth step is the again formation of this sulfoxide. So you can see the repeated steps happening here, right? So here it forms S double bond O pH. So this is the product that we get in this reaction. And again, Sven, the question, if you look at the stereochemistry in the whole process, the stereochemistry of this bond is unaffected. Also, this bond is unaffected uh, uh, in while all these four steps, and we get the after four steps, this intermediate steps. So we get the formation of this intermediate. So this is the pH, right? And if you look at this bond is the above, and this bond is directing downward, right? This is directing downward, and this is directing upward. So in this case, what happened? So although initially the OH was downside, but the stereochemistry is of this bond is vanished here. And in the next step, what happens? So this ring and this ring is in the form of, so it will be these two planes will be in this form. So the plane of this A ring and plane of this B ring. So here is the plane of the first ring, and this is the plane of the second ring. That's why when the attack of this OH, again this O attacks here, and that is the 2,3 sigma tropic, and give the formation of OSPH, right? And which is then again further reacted with this POME thrice to give this SOS SPH OS bond get cleaves, and it gives the alcohol. So the addition of this will take place from the upper side, because the endo attack that endo attack, that is attack from the downside, is not that it sterically not possible. That's why because of steric hindrance, so the attack from the above side takes place, and that's why the stereochemistry of this bond get changes. So this is the mechanism in which what we did, we just change the stereochemistry form, which here OH is directing downside, and here OH is directing upside, by using this rearrangement reaction. So this is the answer for this one, because if you directly look from this step to these steps, there are several in between steps are involved, and again from conversion of these to these, again there are also similarly 2 3 steps are involved to get this final alcohol. So this is the answer for the question, which hope he will get. So yeah, so does anyone have any doubt in this question? Again, also another question. on the stereochemistry of this first reaction. So if you look at the first reaction, which is a Diels-Alder reaction, right? In this Diels-Alder reaction, because the question was not clear whether he is having difficult to understand why this OH, the stereochemistry changed, or why the stereochemistry of this one. So I will explain both these. So because we also have to discuss the stereochemical aspects of all reactions, so better to discuss here only. So if you look at the question, this is the Diels-Alder reaction, and in the Diels-Alder reaction, if you look at there is hydrogen, right, and another hydrogen, green, right? So when the this is the diene, right, and this is dienophile. You can check the spelling, but yeah, this is the diene and this is dienophile. And when the Diels-Alder reaction we perform, so let's say in this case, uh, this was the initial stereochemistry, and when this entire dienophile comes from the top and this is diene from the bottom, so what happens? Or else, if you look at the stereochemistry here of the product, so this S is directing downward. Instead of taking entire all group, I will just show, or better, I will directly show the 3D model of this one. I will just open this. All right. So here there is a 3D model, and so if you look at the transition state happening between the diene and dienophile. So so the bond directing downward, uh, these two bonds are directing downward, right? And this is these two bonds directing outside of this plane. So in this one also, so when the bond which is out and this bond is on the inside is both two which is shown inside, and this diene interact with each other, it forms a it gives the Diels-Alder product, which is this one, but the stereochemistry of this bond and this bond is not clear. So in this case, this comes from the top and this is, let's say, from the bottom. So what happens? Sorry, this is from the top, this is from the bottom. So and here there is a nitrogen. But if you look at this entire group, which is more bulky, so it will be stay away from in this one. So the nitrogen containing, and this one is the CH2 group, which is here, and this is the nitrogen. I will just write the CH2. So the CH2 and this whichever nitrogen which is present, which comes up, both will be a syn, and this will be from this the bond which is double bond. So it will be both will be directing upside, and again the bond, the CH2, this hydrogen is shown in the green, when they since they are inside, so when the new bond is getting formed, so in the new bond, so let's say this is the new bond which is formed, and these are the remaining bonds. So the hydrogens which are present, they will be, in this case, they will be remain on the, Yeah, in this case, they will remain on the top, and the group will be not this one, this SOH as well as the hydrogen which is in the pink. It will be on the bottom side, and the hydrogen, because the group directly inside, they will be when after reaction they will comes up. So this hydrogen will also be comes up because this entire diene is coming from the top side, right? So the top side, the group directing inside the diene, they will be on the above the plane, and the group which is outside, they will be below the plane. So this both group, which include the hydrogen, which is shown in the pink, and OH, this will be a remain on the bottom side of the plane. And similarly, the group from the dienophile, which is this group which is directing and that will be seen to each other. Here in this case, it will be both this entire this 5-member chain, sorry, 5-member ring will be on the top side. So this is like something complex reaction. So uh, that you need a 3D model to understand this one. But yes, the group directing from let's say the group directing inside, uh, they both and the group directing inside and the group directing outside, they will be in the anti-plane. So in this case, the hydrogens and the ES double bond of pH will be the opposite, which is shown here. So hydrogens will be definitely on the top side. So this is the something complex scenario. So this is like a kind of Diels-Alder reaction, which involve the stereochemistry in this molecule. And again, the next one is like the same one, which involve uh, the reaction as discussed earlier. So this S that forms some sort of, sorry, this is the sulfoxide. This sulfoxide from the 2,3 as it is directed downside, so the attack will also takes place from the downside, and that's why. So initially the sulfur was here, so the attack also takes place from the bottom side, and that's why this OH is the stereochemistry of this OH is which is OH is directing down, so which is in the dash bond as shown here in this example. So because the stereochemistry of this starting was the alpha, so the stereochemistry of this OH will also the alpha in this case. So this is the understanding Diels-Alder. There are some I think shortcuts that uh, I think I will include in the next lecture. But as of now, you can consider in this case also uh, the stereochemistry of this directing the group which is inside, and the stereochemistry of the group which is outside. It will remain anti, and in this also the stereochemistry of the dienophile here, so that also will be remain I mean will be changed in the reaction. So these are the some points that in this way the main question was the why the stereochemistry of this OH is remain sorry, the stereochemistry, why the stereochemistry of this OH is alpha. So the reason is in this one, this has the stereochemistry fixed, but which is directing downside, and this entire this CH2 which is up here, the nitrogen is also up. So the and the stereochemistry of this SOPH is directing downside, so that's why the alcohol forms which is which has the stereochemistry directing downside or alpha stereochemistry. So this was the two questions someone has asked, and yeah, these are the some that we have already discussed. Sulfur-based oxidation, which involve the formation of alcohols at this position. And again, we have seen some example which involve the oxidation of using the selenium dioxide. If we have the ketone, it forms the 1,2-diketone. Further, we have also seen the sulfoxide sulfinate rearrangement reaction, and this is the rearrangement reaction. The product, as I have shown earlier, so OSPH, it is in the equilibrium with the S double bond O pH. So that's the reason. In the prior example, there are these many steps are involved, and to form this SPH to S double bond OPH, it get formed. And when such OSPH is interact with this kind of nucleophile or thiophile, which gives the formation of alcohol. So these are the some reaction, and also this is the another reaction, which is which involve the silanes and also the palladium catalyze and the benzoquinone. So the silane in presence of palladium acetate and benzoquinone, it forms a alpha beta unsaturated ketone, right? So this is alpha and beta, right? So alpha beta unsaturated ketone, and with the only E stereochemistry. So that's getting formed in this case. So these are the some reaction already studied, and again we have also seen the selenium dioxide based oxidation of allylic and benzylic positions. Allylic position stands for this is the allylic position. So if you have the allyl group here, the position adjacent to this alkene, which is we call it the allylic position, and also the position adjacent to the phenyl, the CH2 here are this position is the benzylic position. So there are some rules while when we are performing the selenium dioxide based oxidation, and we will just go through directly through all the rules. So just it will be a recap. So the oxidation always occurs at the disubstrate side of the double bond. So let's say we have the uh, this is the double bond, right? And this is the disubstrate and monosubstrate. Oxidation always occur either this one or this one, right? Again, and but the condition is there should be a no bridging alkene. So we have seen one of the example in the assignment. So let's say here there is a bridging. So let's say we have such molecule, right? And let's say there is R anything. So if you look at this one, this is only a disubstrate. Let's take it here. Just take the simple example. So if you look at how many uh, allylic positions for present for this double bond, there is this is the one and this is two. So there are two positions are present, right? So the first and the second, but if you look at and here there is third position. But if you look at the this one and two position, they are the bridging position. So the oxidation doesn't take place at this position. So sorry, yeah, the alcohol OH group will not be goes to that position. But if you look at the third position, although it is monosubstituted, but it is not bridging. So that's why the in this case the product is formed will be in this manner. CH2 OH. This product is formed in such case, right? Again, the second rule is the oxidation of the alkyl cyclohexenes occurs in the ring rather than the outside chains. So let's say we have the such examples, and this is the double one, right? So how many allylic positions are present? So this is the one position and this is another position. If you look at the both the positions, this is also a secondary and this is also the secondary, right? But the preferentially the oxidation occurs at the ring position rather than the outside one. So this is the second rule. And these rules are for those who are preparing for CSIR or GATE, for them it is useful. The another one The oxidation never occurs at the bridging position that already seen. So this is the, let's say we have such molecule and we are trying to perform the selenium dioxide based oxidation. This product will not get this product because the if you go for this we need to go into the reaction mechanism, and in the reaction mechanism there will be a, if it occurs at this position there will be a such intermediate step that need to be formed, and such intermediate step that need to form. So sorry here sulfur, so such intermediate step that need to form, but also if you look at the this Braid's rule, uh, this double bond will not be exist at this breathing position. That's why the oxidation of this alcohol is not possible. So in this case, there is no any allylic position, right? So in this case, the reaction will not go. Yeah. So this is the intermediate that I was talking about. So this intermediate will not able to form because of the Bates rule. The fourth rule is the preferred order of reactivity is expected to be the CH2 react first, then the CH3, then the CH. So if we have some example, so which involve, so this is the allylic, and let's say here there is CH, here there is CH2, and here there is CH3, and let's say here there is any R which doesn't have any allylic position. Let's say here uh, any other group. In this case, the order will be the CH2 will react first, CH2 OH is will be the preferential product in this case, in and the remaining product in this case will be any group. Here also any X group, right? So we got carbon quaternary. So in this case, the preferential order of the uh, reactivity will be in this manner. And another rule is another point is the a diene rather than tertiary alcohol is expected to result in case of preferred position is tertiary. So let's say we have such starting material and we are trying to perform the selenium dioxide based oxidation reaction, and we let's say there is on one side this allyl equation is the tertiary, and here there is a secondary, right? Sorry, this is the tertiary and this is the quaternary. And in this case, what happens when you perform this reaction? So first step is obviously that we seen the sulfoxide Se double bond OH formation, followed by, let's say if you want to perform the oxidation in this side, it will form the intermediate between all the O SeOH bond formation. But the conversion of these to this will not occur. But in equivalent, we have such intermediate which have the, this is the CH3, right? So one of the hydrogen get abstracted by such reaction. This is also a kind of sigmatropy rearrangement, we can say. And in this one, this O, this will be negative and this will be positive. This O abstract the proton followed by the double bond formation and shifting of this double bond, which is already there. It gives the elimination of SeOH twice and gives the diene as a product in this case. Sixth one is the allylic rearrangement can be observed in such reactions. Let's say this is also possible product. So we will get in most of the cases, many of the cases, this can also be observed as a product in which the allylic rearrangement takes place. So we have such allylic positions, and it forms the SeOH as shown here. The first formation abstraction of proton followed by the SeOH bond formation, and this SeOH will again, this OH attacks here, this bond goes here, and this OH Se again get back to forms a migrated intermediate, that is SEOH group, entire group is getting migrated from this position to this position. So that can also occurs in such reactions. So these are the some points. And yeah, here another example. So if there are two similar preferred positions on the both side, then obviously there are two possibility. It will oxidize on the both side. That is, we get the mixture. So let's say uh, this is the product, and there are two similar positions. Let's say here R is any other group, R, and R1 and R2 is different. So in this case, both this product and this product will be the same, right? But if you look at the when there is R1 and R2 are different, so it will form first here. So we get this product. Also, it can attack to the second position. We get the second product. So we get the mixture of product. So these are the some points for the selenium dioxide based oxidation reactions. So that also need to keep noted. And also while solving the assignment question, you can also uh, note this point. And further, as this SeO2 based, this is the mechanism that you can just refer back. It's already in the week, I think week like lecture, I don't know, but it is already there in the lectures. So the mechanism of this one for all previous reaction that already reported. This is the another type of this SeO2 based oxidation, in which the, let's say if you have the starting is the diketone. Sorry, the starting is ketone. So when ketone is reacted with the selenium dioxide, it forms uh, enol, right? Let's say we have the acidic condition and this ketone. So this ketone can convert it into the enol. In this form, and when this enol is formed, this enol is reacted with the we have already there SeO2 in the reaction. So as the previous that we studied, so this will this hydroxy group will interact with this one, and this O minus is formed, right? So it will be O, Se, O negative, double bond O, right? And there will be a double bond. And in after this one, so what happens? This O negative again here can interact here from here, and again it forms the intermediate, which is double bond O. Yes, here double bond O. O. Sorry, in between there should be in between oxygen, right? In this case, there will be O, then S double bond O. Here there is OH. Not OH, it will be O negative. And this O negative, let's say there is a proton. So this O negative abstract the proton, and followed by the bond pair of this carbon hydrogen bond goes to the in the formation of carbon double bond oxygen, and again the bond pair of between the oxygen and sulfur goes on the sulfur, so it will give the oxidized product. So in this manner we get the formation of diketone by using the selenium dioxide. So this is another type of another utilization for this selenium dioxide already seen. First one is the oxidation of these two, this, and another, this was the first and this is the second one. So these are the some reactions that we have already seen. And to solve some problems which is included in the assignment number 2, so I will just added some slides. Here there is the sulfine sulfonate rearrangement reaction, and as already mentioned, we have such sulfur that already discussed. I don't think need to discuss, which is always be on gentle warming, or even in some cases at room temperature also. We call it as RT. So at room temperature also it can be converted into this such sulfoxide. So the allyl sulfonate can easily convert into sulfoxide and vice versa. And further, we have already seen some examples earlier. So I will just directly show that example. So this is the one example that we have already seen. Yeah, this one. So how uh, uh, this alcohol converted to this one by using this sulfine sulfon oxide rearrangement reaction, right? So I don't think we need to discuss that one, which in this reaction involve the 2,3 sigma topic rearrangement that we have already seen. So I will show again. So this is the 1, 2, and 3. So this is 2, 3 sigma topic. So in this one, why 2, 3? That also important question. So why 2, 3? Does anyone know? So this is 1 and 2. So these are the two bonds here. 2 and 1, 2 and 3. So there are three centers, right? So this is also we can call, or also there are number of electrons involved. If you look at based on that one also, it is 2, 3 sigma tropic reargumentation. So okay, not in this manner. The numbering should be, so this is the 1 and 2. Here it is 1, 2, 3. So this is the 2, 3 sigma tropic. That also, I mean, there are different nomenclatures. You can see multiple explanation for this one. But yeah, it is a 2, 3 sigma tropic. So Diels-Alder is, so what is Diels-Alder is 4 plus 2, right? This is 2, 3 sigma tropic. So this is the mechanism that I have already pasted here with some of the examples. I don't think we really need to discuss this one, but the favor transition state geometry, that also eh, that again I would like to highlight here. So let's say we have such we have the we are performing 2, 3 sigma topic rearrangement reaction, and let I will just minimize this. And we have what we have here. So we generally perform 2, 3 sigma topic on this, which involve a transition state. So let's say we have such 1, 2. Here there is another R3, and again here there is a group which has which which have the again R4 and R5 also, the yes SR, or also we can sorry, initially it will be OSR, right? But as we seen earlier, this OSR is in will be in equilibrium with the S double bond O R or AR. I will just, for simplicity, I will just add here. It is like some different group. It is AR, let's say. So it will be in equilibrium, right? And how the 2, 3 sigma trophy happens. So in this case, the negative charge attacks to here, followed by the migration of this electron, and again the cleavage of this bond, and we get the product which has the which is so it will be OSAR. Also, there are two groups, which is R2 and R1, and the double bond forms in this one. So which has again, here there was R3 initially, and here there was R5 and R4. So the geometry of these groups are important here. So as of so here I have written R3 and R5, they are anti to each other, right? Uh, that is in the form of trans to each other. So how this geometry is getting uh, for this molecule. So there is a intermediate transition state. I will directly show that transition state. Just I will just uh, so in this case, so let's say we have different functional groups, and particularly in this case, the groups which is highlighted in the I am highlighting the R3. This is the X group, any X group, and there is R1 and R2 groups. So let's say there will be any condition. So in this one, so I am taking the condition in which R1 is bulkier than R2. So R1 is bulkier than R2. So this R1 will be in the pseudo equatorial position, because if you write this transition state, so this R1 will goes here in the transition state. Again, this as R1 is bigger, right, than the R2. That's why I have written that one in the into the pseudo equatorial position, not taken in the axial position, right? So another one is the, if you look at this X and R3, this X and R3, they are seen to each other. So this was the initial double bond, right? And this is the X. Sorry, this is the X that I am highlighting. So this X and R3, so they should remain seen to each other. And again, what we have here, this hydrogen and this entire group also seen to each other. So if you go from this double bond, so this entire hydrogen as well as this entire group. So the group which is like this entire group which is seen to each other, that we have already drawn, right? So this condition that in the transition that we need to keep in mind, and we'll also see yeah, so this is the condition because when we have the bulkier group, that will goes to the equatorial. So always try to do that one. So bulkier group will be in the equatorial position. Also, the keep the geometry of this double bond same. So in this case also, the geometry I have kept the same, and we perform the next reaction. Sorry, the perform the next step. So it will be, so the O minus attached to this side, the group here. So in this one, this OSR, this entire group is formed. The X, so since there is hydrogen, that hydrogen not drawn, but there is another X. But here, only keep in mind the state. I mean, we have to only see the not, we don't require to see the stereochemistry of this, or the absolute configuration of the center. That's the next part. But as of now, we are only focusing on the stereochemistry across the double bond. That is which group is goes to cis or anti to with respect to other group. So in this one, so the R3, which was directing in this one, let's say R3 as well as R1, they both are directing upward. So these two groups should be on same side, R1 and R3, right? So this is the R3. So these two groups should be on same side, and another this entire, this R2 and this entire group, which is this one. So this CX bond and the other alcohol, and yes, this entire group should be on. So this entire group, so here in this case, this entire group should be on the same side. So you need to check the options here. So whether we have already drawn the correct one or not. So here R1 and R3, they are on the same side, and this group R3 and this sorry, R2 and this entire group is on the same side. So we have written this correct stereochemistry for this one. So this is how you need to take into consideration. I will just take the question which is in the assignment, and so we'll just directly solve that question here only. So we have one question in the assignment. This is the question, right? I will just take this question. So if you look at the question, what question says, in the typical sulfoxide sulfinate rearrangement reaction shown below. So the reaction that they have shown, we have the sulfoxide. This is the sulfoxide entire part, and uh, the intermediate steps for this one. So here, what we can see is pH group and Me group, methyl group, is seen to each other, right? So the transition state which has this pH and methyl group seen will be the correct transition state, the first one. So the group which is in the seen side, which is on the same side, which will be seen in the transition state. So if you look at the transition state, so let's say we have the transition state here. So if you look at this group, this pH directing beta, methyl directing alpha, that is downward, pH directing upward. So this is wrong transition state. If you look at the another transition state in which the methyl directing upward, phenyl directing downward. So these two transition states are wrong, right? So we have neglected two options in this one. Another one is, let's say we have this groups directing on the same side, right? And the groups like this hydrogen and this entire group is directing on the same side. That obviously, if this methyl and pH, so this methyl and pH directing same side, here also directing same side, here also directing same side. Okay, now we have to move to the next steps. So in the next step, what we will see, the bulkier group should be on pseudo equatorial position. So if you look at the another one, the bulkier group should be pseudo equatorial, right? So here, among the, I will just rub this one. Among this group, the group we have methyl and isopropyl, right? So the isopropyl I will highlight in the red, and methyl group methyl group is in green. So methyl group and isopropyl group, which group is bulkier? Obviously the isopropyl. Isopropyl group is like this, CH3, and this is the isopropyl group, right? And methyl group is like simply CH3. So among these two group, the isopropyl group is bulky. It should be on pseudo equatorial position. So if you look at this transition state, which involve the isopropyl group at axial position, here also the axial, which group is axial? So in this case, the isopropyl group is equatorial, right? So this transition state is correct transition state in this case. So, and as the isopropyl group is bulkier than the methyl, right? This is the definitely bulkier group than the methyl. So that's why it should be on the equatorial, and this is the case in the fourth option. So the option D is correct option here. So this is the one of the question which is in the assignment that we have already now discussed, right? Yeah. So anything else in this one that we need to discuss? Uh, yeah, this is the, I have added some slides based on the Diels-Alder reaction mechanism that you can refer from the drive. This question we have already discussed. Why the stereochemistry of OH. Again, there is another the mechanism of sour oxidation that we have already discussed in the our last lecture, right? And in the last part of the this video, we have discussed the in the lectures from 9 and 10 lecture, 10th lecture maybe, we have discussed about the Des-Martin per iodine based oxidation. So what is the short form of this one is DMP, and we call it as a DMP oxidation, and which refer to the this reagent. So this reagent is the Day's-Martin periodate, and which involve the iodine atom, which is attached to the OAC. And five, let's say here there is let me draw entire structure. So this is just general, this is basic structure of this DMP, and there are many other variant of this reagent also. Let's say IBX. Uh, so uh, the question is nomenclature. How do we nomenclature for this one? So you have seen some question in the assignment also. So you may see the 12I, 5, 10I, 4, this kind of nomenclature for this one. So let's say we will give the nomenclature for the reagent that we have drawn here. So how to give the nomenclature? So in this one, first let's highlight what this really stands for. This stands for 12 number of electrons are used in the formation of the bond or in the valence shell. The one this is the iodine, obviously, because the electrons across the iodine, and this 5 stands for number of bonds. So let's say take this example of these molecules, and if you want to give the such nomenclature, so what I will give, there will be obviously in between I. How many bonds are there? 1, 2, 3, 4, 5. There are 5 bonds, so there it is 5. And how many electrons? So one bond involved 2 electrons, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10 I5 in this one. And obviously there will be electron. Let's say there is no lone pair of electron, then in that case, in that scenario, it will be like this. But there will be a one electron pair. So that is it not shown here. Let's say here there is one electron pair. So in that case, what will be the nomenclature for this one? It will be 12I5. So this is how the nomenclature of this one that we need to give. And don't get confused between the structure, because in the question uh, it is showing some different compound. Let's say like this iodine based molecule, polyvalent iodine. And if you look at the structure, I will just zoom the structure. So if you look at the structure, how many bonds are there? So 1, 2, 3, 4. So there are 4 bonds, right? Again, how many electrons are involved around here? So there is 1, 2, 3, 4, and lone pair of electron. There are total 10 electrons are there. So it will be 10I4. So this will be the option you can select in this case, right? So we'll see some. So this is the about the Day's-Martin per iodine based oxidation and how this oxidation occurs. So let's say we have the any molecule, any alcohol, and from this alcohol, if we perform the DMP oxidation, let's say we have these R1 and R2 OH, it converted into the keto. So here you can see the mechanism. So this alcohol lone pair of oxygen is interact with the iodine, and OAC groups kicks out. So in this case, OAC get removed. This is the general SN2 reaction, and so this OAC is initially in the first step is get removed. And let's say we have the hydrogen here, so which is shown here. See though this eliminated OAC is abstract the proton followed by the electron transfer shown in this manner, and we get the ketone product as well as the this as a side product in this reaction. So also keep always noted the what are the side products formed in the reactions. So as I shown, In the Swan oxidation, there is, I have the mechanism correctly here. So this was the some byproducts that forms in the Swan oxidation: CO2, CO, DMS, D. So in the Swan oxidation, these are some byproducts that also you need to keep noted. And in this case, IBX, sorry, the DMP based oxidation. So this is the byproduct which is getting formed in this one. And if you look at some examples of this one, so let's say you have such molecules and want to perform this is the example of the uh, geraniol, and which can convert it into using this DMP based oxidation. In the solvent will be the DCM in this for this, and in the room temperature it converted into the uh, geraniol around 84% will give the alcohol to aldehyde. So this is the utility of this reagent. The another uh, is the this was the that we have seen the DMP, and there is another reagent which is we call it as IBX. Uh, let's say here I will just have which I have shown here. So this is the benzoic acid. So this is also useful for the formation of this is the intermediate and which is formed in between before the formation of DMP, and this IBX can also use for the uh, oxidation of this alcohol to ketone. Someone asked one of the question that I have. Yeah, this is the question someone has asked in the question and answer forum. So why this hydroxy group is what is the driving force behind the elimination of this hydroxy group in these steps? So this is the mechanism as shown earlier, which is from the convert from the hydroxy to the keto using the IBX with a similar mechanism as like DMP. And so this is the intermediate steps that's getting formed. So which in all intermediate, right? And yeah, so alcohol to keto, keto to enol formation in this one. So this was the intermediate steps which involve the elimination of this hydroxy group. Why this is why although hydroxy group is badly in group, but still here it is getting eliminated. So someone was asking reason behind this one, because this get removed from this iodine, because if you look at the some criterias or the some uh, points. So in this kind of oxidation reactions, the presence of catalytic amount of tosyl hydroxide, which is slightly acidic. So this slightly acidic condition helps to or accelerate the reaction. What does it mean? It accelerates reactions means definitely the presence of acid. What will happen? It will be this OH. It will be present in the H2 plus format, and either this one or this one, and which is present in OH2 plus format, that group will be that hydroxy group is getting eliminated in this one. So the acidic condition is there. That's why this will be not bare hydroxy negative. It will be in the form of H2O is getting removed from this one. It is just a catalytic amount, and presence of base. Base means there will be no such OH plus formation. So in this one, as shown here, there will be a OH2 plus formation. But if there is a base, then this will be not formed. So that's why, because of this slightly acidic condition, this OH minus, which forms later H2O, it get eliminated in this. So that was the driving force behind the uh, in this step, for the this step from the conversion of this to this hydroxy get eliminated and get forms the this ketone. All right. So this is all about today's lecture. So I hope you will able to solve the all assignment question. There is not that much difficulty, because if you look at the questions, so what it mentioned that we already discussed the selenium dioxide based oxidation here and here in this case. So where there will be a oxidation, definitely it will be not on the bridging position, right? So this is obviously the wrong answer in this question. The another one is this also wrong, because they have written the double bond. So you can easily able to get up to the final product in this case. The second question is the major product form in the following reaction. So this PHMG Br, but make sure you consider the role of copper bromide. So the only sole PHMG Br is the uh, hard, you can say hard nucleophile. So it attack on the hard kind of electrophilic center, that is the hard center, that is carbonyl one. But when you add the copper, so what happens? That I don't think you need to in this case, not this one. PS negative directly attacks here, but when you add the copper iodide, so it will definitely attack on the soft center. So that point you need to keep into consideration. The next one is like the DMP oxidation. So in this case, DMP oxidation of 1,2-diol, the major product formed in the following reaction. So we have here tertiary alcohol and here another one, secondary alcohol. And if you look at this one, so what happened in case of DMP oxidation? So it will be, this is the definitely the oxidation at this position is not possible, right? Uh, so in this case, so this is the one product that I think this will be the product, but you can go through step-by-step mechanism. This question that we have already discussed, that we have initially we have neglected uh, we have neglected two possibility, because which has the definitely the wrong stereochemistry mentioned in the transition state of this double bond. So and remaining two that we have among the two that we have eliminated this one, because the bulkier group is isopropyl and it should be on the pseudo equatorial position. The fifth question is the based on the following allylic oxidation with the selenium dioxide. So that obviously I don't think you need to tell the which step is getting which intermediate is forming in this one. That we already discussed, right? Because when the selenium dioxide uh, react where it forms the selenium oxide, and then for the next step the typical allylic sulfinate ester in sulfoxide sulfinate rearrangement. So you can able to select that one. So definitely, so you can able to get that one, right? So this is the intermediate. Another question is based on the conversion of allyl alcohol 1 to allyl alcohol 2. So 1 to 2, that conversion based on the sulfine sulfonate, again that already discussed, but I don't think we have discussed this question, but hopefully you will get the answer. I don't think there is much difficulty in getting this one, and this also we have already given the answer. So uh, I don't think so. I will upload this slide on the portal, and uh, if someone let me know, uh, so are you able to access the OneDrive or not? So I will just put the link of the drive, and you can just name the book that you want. So I will upload the PDF of that book. Mm. I just copied link, and you can get the link from this one also. So you can keep this link saved. All right. So which the PDF of which book you guys want. I will I can send the I have much I mean many of the essential books which are required for the I mean for masters as well as PhD. So I will upload that books here. So if you guys have any doubt, then that you can copy that link that I have pasted in chat box, and hopefully you will able to access that one. And I will upload the slides that of the every week, as well as I will upload there some study material which include the reference books, like I will upload Caruthar, as well as the for the name reaction there is J. Jack Lee, and any other book if you want I can upload there. So does anyone have any doubt as of now that the course that topics that covered by professor? If you don't have any doubt, you can leave the meeting